So easy access to physical, chemical properties and rigorous thermodynamic in Excel. ProSim is a European engineering software company delivering chemical process simulation software and consulting services since 1989. Our competencies and core expertise are in process simulation and optimization. So our main offer are software about chemical engineering software editors. And in addition to our simulation software, ProSim offers a full range of services. Among these services, we provide training, maintenance, and support. So we don't leave you alone with the software. We also offer process studies through modeling and simulation. We do also application implementation and software extension to fit your tailored needs. We do specific software application development and support and maintenance of legacy code. ProSim solutions are used to improve process design and increase plant efficiency and reduce the impact on environment. As you can see on the screen, we have a consistent suite of software. Today, the focus will be about our thermodynamic tool, Simulis Thermodynamics, which is an add-in in Excel. Besides our thermodynamic tool, so you can see that we do simulation and flow sheetings. Our main product is ProSim Plus. We have specific software such as ProSim Plus HNO3 dedicated to simulation and optimization of nitric acid plants and nitrous vapor absorption. Sorry about that. We do also simulation of batch processes, heat exchangers, and we do also energy management and dynamic simulation. Our headquarters is based in the south of France in Toulouse. We have a subsidiary also in Philadelphia in the US. We have a network of distributors located in various countries, and we have over 1,000 customers in 73 countries who are operating companies as well as engineering and construction companies or equipment manufacturers in all process industries worldwide. Thanks to long-term partnerships with major research centers, ProSim continuously develops innovative software and has become a major player on the international market. I will let Olivier also complete the information about our network of partners.
So hi everybody. ProSim is a spin-off of the NCSET Chemical Engineering School, and so we are very close to the research lab of this school, which is the Laboratoire de Génie Chimique of Toulouse. We also have collaboration with the other main research center around chemical engineering in Nancy, LRGP, and we work with the team of the Professor Jobert, who developed a thermodynamic model which is predictive for an equation of state based on PR, which is called PPR 78. We also have collaboration with UCA in Clermont-Ferrand, with Professor Dussap around electrolytes. He developed a predictive model which is called ULPDHS, based on Unifac-Larsen for electrolytes, and also he worked with Cosmo methods for carbohydrates molecules. We also have collaboration with the School of Mines in Paris, with Professor Christophe Coquelet, and we just finished a research project on refrigerants with Arkema. We also work with UPMC and LSPM in Paris with the team of Professor Passarello and Professor Simona. and we collaborate with the French Petroleum Institute with them on a project around the PPC-SAFT equation of state. We also have collaboration with the ENSTA lab with Professor Patrice Parico, mainly for development around Cosmo-SAC methods and also SAFT VRME. And we also have collaboration with the University of Mediterranean with the team of Professor No, who developed a model which is predictive for very asymmetric mixtures with water and hydrocarbons. We also are a member of the UNIFAC consortium of the Professor Melling, who managed the different versions of the UNIFAC matrix. We are also a member of the COLAN network. I will come back to Cape Open aspects later in my presentation. We are also a member of the consortium in Denmark from the DTU, which was the former CAPEC consortium. We are also a member of the deeper consortium from the AICHE, which is considered as the gold standard for pure component properties. We also have a collaboration with the DECEMA, which is a German association which developed databases for mixtures experimental properties. As I said previously, we also have a collaboration with the French Petroleum Institute in France around the SAFT methods. We also have collaboration with a German company, Inosim, which is developing software for dynamic processes of production logistics, which can be linked with our batch reactor and batch column software. We also have collaboration with Fifth Cryogeny, manufacturer of plate fin heat exchangers, and we developed with them for several years a software for the modeling of this type of equipment. And we also have collaboration with Total and Rocket around thermodynamic model development. The outline of the webinar today is first, we will try to explain you how you can use Simulis Thermodynamics inside Excel. First, I will have a look at the pure components properties. I will explain how to select these components in standard databases. Then I will explain how to create your own components from experimental data or directly from the molecular structures and using our estimation methods. I will also explain how you can use Simulis Thermodynamics to analyze thermodynamic properties. And also I will show how it's easy to create your own databases. Then we will go to mixtures. I will show you how you can select and configure your thermodynamic models. That means model selections and also parameters selection. And I will show you how to use Simulis Thermodynamic services in order to analyze your system. Then I will do a short demo in Microsoft Excel, and you will see how to get information from the calculator and how to use thermodynamic functions and build your own calculation spreadsheet. So Simulis Thermodynamics is based on a software component approach. That means that the same software can be used by several other software. It is available in French, English, and Russian version, and for 32 and 44 byte systems. What is included inside Simulis Thermodynamics is first thermodynamic functions, which are used to compute mixture thermophysical properties like transport properties, compressibility properties, thermodynamic properties, or non-ideal properties. For example, you can compute compressibility factor or entropy or exergy and so on. And what is very important to note is that you can compute the property, but also their derivatives with respect to temperature, pressure, and also the number of moles. That means that Simulis Thermodynamics can be used to build your model and then compute the Jacobian matrices. Then also included inside Simulis Thermodynamics are the flashes, which are used to determine the phase of the mixtures, considering temperature, pressure, and composition. You have vapor-liquid equilibrium calculation. To compute a flash, you have to know the composition of the mixtures, but also two different variables between temperature, pressure, vapor ratio, molar volume, enthalpy, entropy, or internal energy. And so what you can see on this slide, the matrices, you can compute any kind of flash mixing two of these properties. Using Simulis Thermodynamics, you can also compute phase envelopes and also properties like rate vapor pressure and true vapor pressure. You can also compute liquid phase demission, and also you can have flashes with a vapor phase and two liquid phases. And also you can have calculation with a vapor phase, a liquid phase, and a solid phase. Then included also inside Simulis Thermodynamics, you have databases for pure components. Simulis Thermodynamics includes the deeper database, and you can include as many user databases as you want. There are also databases for binary interaction parameters for system for models, which require this kind of information. And Simulis Thermodynamics can be linked with the data preparation package, which is a software which is provided by the DKMA. Regarding databases, we supply the most recent public release of Deeper, but also the previous releases that can be used in order to make comparison with components from the previous release. And also you can be sure that you can get the same results with calculation you have done some years ago. For pure component properties, you can of course access all the properties which are included for all components. You can modify them if you want. You can also plot the temperature dependent properties. Included inside the software, you have a tool to regress your own experimental data or experimental data from the literature. We also provide methods for the prediction of intrinsic but also temperature dependent properties from the molecular description of the molecules using the SMILES, which is a very common way to describe the molecular structure of the molecule. The SMILES can also be used in order to generate all the group contribution predictive model decompositions, such as, for example, PPR78 or for unified methods. And Simulis Thermodynamics includes also tools to calculate petroleum fraction properties. Regarding the binary interaction parameters, for models which require this kind of information, like for example, for activity coefficient model like NRTL, or equation of state like Peng-Robinson or Reddish-Krung-Suave equation, we provide libraries for this information. But you can also fit this information from experimental data using the data preparation package from the DKMA or using Simulis Thermodynamics inside Excel. Of course, the most important part of a thermodynamic server is the library of thermodynamic models. Roughly, there are two different approaches to describe thermodynamics phase equilibria and thermodynamic properties. One is called the homogeneous approach. That means that you will use just one equation to represent all the phases which are present in the mixture. This equation of state presents several advantages. You need a few data. That means, for example, for cubic equation of state, you will need only critical temperature and pressure, eccentric factors, and binary interaction parameters. And if you want to do some enthalpy calculation, you need also the ideal gas heat capacity. And there is no limitation in terms of temperature and pressure. But there are some drawbacks also using this kind of approach. The main drawback is that when we use van der Waals mixing rules, this kind of equation of states are very often limited to low polar components. So the other way to represent your thermodynamic system is the heterogeneous approach. That means that you still use an equation of state to represent the vapor phase, but in order to take into account the non-ideality of the liquid phase, you will use an activity coefficient model. There are some drawbacks of this approach, which are the limitation in terms of temperature and pressure. Given that you use two different ways for computing the liquid and the vapor properties, you cannot use this method when you are close to the critical points. So That means that we try to develop and implement every year new models, and these developments are linked with several ways, which are: first, we try to have new mixing rules for equation of state. We will have some explanation after that. We also try to have models with more physical basis, like fast equation of state. We also implement some specific models for specific systems. And given that there are a huge number of molecules in the nature, we also try to implement more and more predictive models. If we have a short explanation about equation of state approach, here you have a phase diagram for two components, mixtures with methane and benzene. The pink curve represents the vapor pressure of the methane. The round circle here is the critical point, and the yellow curve is the vapor pressure of the benzene with its critical point here. Above the curve, you are liquid, and if you are under the curve, you are vapor. From the knowledge of the pure components properties, if you want to know in the pressure temperature plan what is the phases which are present for your system, you need to use an equation of state to compute what we call the phase envelope. That means in blue the bubble curve, and in red the dew curve, and both curves are crossing at the critical point of the mixtures. Above the blue curve, you are in the liquid phase. Under the red curve, you are on the vapor phase. And inside these curves, you have both liquid and vapor. This kind of phase envelope are very useful, for example, when you do some gas transportation. In this slide, you can see mixtures with mainly methane. That means 99.99 mole% of methane, with just a small amount of impurities, which are nonane, ethylbenzene, and dimethylcyclohexane, only 0.01 mole%. And you can see that the shape of the dew curves are very different. If we are at 40 bars, for example, if the impurity, is the N-nonane, that means that if the temperature is less than -8 degrees, there is a liquid phase which can appear. If the impurity is the ethylbenzene, in that case, the dew curve is around -20 degrees. And if the dimethylcyclohexane is the impurity, in that case, you can go to -40 degrees with no liquid phases. The problem is that when we use equation of state, like for example SRK, to try to represent mixtures with polar components, like the acetone water mixture, in that case, you can see on that graph experimental data, which are the triangles, and we plot the vapor fraction with respect to the liquid mole friction. And if we use SRK, you can see that the behavior is not the one which is in the real case. So in that case, what we have to do is to use activity coefficient model to represent the non-ideality in the liquid phase. And in that case, you fit binary interaction parameters and you obtain values which are close to the experimental points. The problem with that approach is that what can we do if, for example, the temperature is above the critical temperature of one of the components, because the vapor pressure is not defined. And so that means that the alternative approach in that case is not an answer. So researchers developed in the 90s of the previous century new mixing rules. So they started with cubic equation of state based on the Reddish-Krung or Peng-Robinson, for example, equation of state. And they developed mixing rules. The first one was developed by Vidal from the French Petroleum Institute. And there was modification by Mikkelsen, by Menning, and so on. And inside the attractive term, the Gibbs excess model is included, and this model can be one of the previous models described, like Wilson, NRTL, Uniquat, or predictive model like Unifac. That means that this is an equation of state approach, and which is able to manage polar components also. So if we come back to our mixtures with water and acetone, in that case, we use, for example, the SRK equation of state with the mixing rule MHV2, using the NRTL model with the binary interaction parameters, which were fitted at 1 atmosphere using the NRTL approach. You can see with the red dot line that you still very well represent your data at atmospheric pressure. But what is interesting is the next slide, is that if you use this model with no more information, you are able to predict the vapor-liquid behavior at elevated temperature and pressure. And if you have a look to the red curve, in that case, you are above the critical temperature of the acetone. So that means that this kind of model is predictive at elevated temperature and pressure. So regarding the library of thermodynamic model included inside Simulis Thermodynamics, you will find classical equation of state like Redlich-Franck-Soivet, Pang-Robinson, and so on. You can select several kind of alpha function. You also have other equation of states based on corresponding states, for example, like LKP, or based on hard sphere like Nakamura. And you have also soft equation of states, and so on. Also included, you have a lot of activity coefficient models, including all the models developed by the Unifac consortium, which are predictive models, but also other predictive models, like, for example, the Unifac model developed by the NIST. Regarding complex mixing rules, I spoke before, you have several mixing rules. You can link any cubic equation of state with any Gibbs excess model. We also include specific models, mainly for associating components, like pure water, for example, but also for carboxylic acids for dimerization, or for systems with water and formaldehyde, for example. And we also have a library of electrolyte models. Also included inside the software component, you will find a graphical user interface. This graphical user interface can be used to select your components from the database. You can modify these properties also, you can compare and so on, but also to configure your property model. And what is important to note is that there is no black box inside Simulis Thermodynamics. That means that anything you want to change, you can change it. The last part, what we call the services. For example, to manage the unit conversions or to have interactive calculation. For example, directly from Simulis, you will be able to compute fluid phase equilibria, or also residue curves for in order to manage your distillation. And all these things, as I said before, are included inside the components. So that means that any software which embed Simulis Thermodynamics will be able to access any of these functionalities. Simulis Thermodynamics is used as the heart of all our software. That means ProSim Plus, for example, for steady state calculation, or batch column for calculation of batch distillation. Simulis Thermodynamics is also available as an add-in in Microsoft Excel. We will have a look of that in the next presentation, part of the presentation. And that means that you will find several hundred of new functions which are related to thermodynamics. You have also a toolbox in MATLAB. So that means that you will access the same thermodynamics in Excel and in MATLAB. You can also export your results to Microsoft Excel or in some formats which are used by software which requires some tabulated data. We provide also with Simulis Thermodynamics an application programming interface. That means that you can use Simulis Thermodynamics inside any programming language like C++, C#, Fortran, and so on. And so some of our customers use in their own software Simulis as a Thermodynamic server. We spoke very shortly about Cape Open. Cape Open is a standard which was developed in the middle of the 90s in order to have interoperability between software providers. It was a European project at the beginning, then it became a world project, and today this is used in order to have one software which is able to communicate with another software. And so that means that you can use the thermodynamics from Simulis inside some software of our competitors, like for example Aspen and so on. And the last part is the link that I spoke before with the Dekema software data preparation package. So when you see this slide, you can see that using Simulis Thermodynamics, you will be ensured that you will have the same way to describe your thermodynamics. That means that you just have to learn how to use Simulis Thermodynamics, and you will have always the same results, given that you will use the same software component. What is important to note also is that Simulis Thermodynamics can be enriched. First, you can add as many new databases as you want. So you can add new components from experimental data that you have, and you have inside Simulis Thermodynamics some fitting tools, but you can also estimate the properties of this data, of these components, using their structures. You can also include your in-house property databases. In order to that, you have to provide us with the interface format of your database. Then, thanks to the Cape Open link, you can also use inside Simulis Thermodynamics a Cape Open package coming from some of our competitors, like Aspen, for example. Then we can also develop some specific library for you with a specific interface. For example, we developed something like that for Air Liquide, which has a specific model for the air distillation. And of course, Air Liquide is the only one which has the ability to access this model. You can also implement yourself your own model using a very simple language, which is the VB script. And in that case, you can access to all the thermodynamic properties. That means pure component properties, but also unit conversion and so on. This kind of feature can be very useful, for example, if you want to add a new mixing rules for viscosity or for thermal conductivity and so on. That means that with just some few lines of code, you will be able to have the exact behavior of your mixture. You can also provide some new models using the expert mode GLL. In that case, for example, that can be used by people who has already developed some thermodynamic models, and then this model will be used inside Simulis Thermodynamics. And if you want, you can use our flashes to compute fluid phase equilibria and so on. So at the minimum, you can develop an activity coefficient model or an equation of state, and you will be able to combine these models with the native models included inside Simulis Thermodynamics. And the last part is that you also have inside Simulis Thermodynamics a socket which is here to use directly the RefProp library from the NIST. Okay, so here you have a different way to enrich Simulis Thermodynamics with your own model or model coming from other providers. So I will now go inside Microsoft Excel. So when you have Simulis Thermodynamics, in the add-in tab, you have this menu, and you can insert a Simulis system, for example. In fact, Simulis is like the Russian doll. That means that at the earth, you have the unit management. Then above that, you have the compounds, Simulis compounds, which is related to the properties of the components. Then you have a Simulis compounds, which correspond to the list of components. Then the Simulis calculator, which corresponds to a list of compounds plus the model which is used to describe these mixtures. And then Simulis calculators, which correspond to a list of calculators. So we will use today a Simulis calculator. You have to select the place where you want in the Excel spreadsheet you want to put the Simulis object. You can add in a Microsoft spreadsheet as many as Simulis Thermodynamics object as you want. And when you click on the Simulis button, you will see what you see here is what you would see in any other application, like ProSim Plus, for example, or in MATLAB. So first you have the compound tab, and in that tab you can select the components. On the red part of the screen, here you have all the server I have on my computer, and I select on this server which one I want to host when I will look for a component. So for example, I will do a search of water compound, and in the two databases I selected, I find this component, and I will double click on this one, and then it will copy from the standard database the component and put all the properties inside the Simulis calculator object. Then I will search for ethanol, and I had also ethanol. You can have a mixture of as many components as you want. In that case, I will only do the demo with two components, the water and the ethanol. Then, if you go to double-click to the components, then you have access to their properties, their structures, some information about the identification, the specific name, the cast number, the family, the SMILE, and so on. You have also information about group contribution methods. You can see all the group contribution methods we have here. You have also atomic properties. You have phase change properties. And what you can note is that thanks to the Simulis system software components, for example, for the critical pressure, here you have all the corresponding values for different units. Regarding the temperature-dependent properties, here, for example, if we have a look on the vapor pressure, here you have the equation which is used. On the right part of the tab, you can see the formulation of the equation. And here you have the range, validity range for the correlations and the coefficient A, B, C, D, and E. Here you have the values which are tabulated from the minimum temperature to the maximum temperature. And here you have the chart. Of course, you can change the unit if you want. You can also change the scale, for example, here. And you also can compute, if you want, the value at different temperature. Then I spoke before about services. Here, for example, you have services about components. You can do some comparison on the properties. For example, properties depending on temperature. We will select the vapor pressure, and we will compare the properties for all the components, and which can be useful if you want to see which are the more volatile components, or for example, if there are some Bancroft points, to see if it could be some azeotrope in the system and so on. You can also compare the components if you want. That means that, for example, if you clone components and you have some properties which are changed, you can see where are the differences. If you have done some change, you can compare with the original. That means that Simulis Thermodynamics will say to you if there are some changes which have been done from the data from the database, between the database and the calculator. And you have also the editor array, which is useful when you want to compare some components and see what are the values for the one and the other. Regarding the databases, this is very easy to publish a new database. You have this button, and then you enter here the name. You click on OK, and you have a new database. You can also save the compound package as a compound file, and then you will be able to open this compound file from any other Simulis object. Then, when you have selected all the components and check if the properties you are using are the correct one, you can go to the model description. On this tab, you see several things. You have different categories. For example, in our case, we want to use an heterogeneous approach. And that means that the profiles which are available above this are restricted to all the heterogeneous approach. I will select, for example, the NRTL profile, and every field using this predefined profile. But if you want, you can change, for example, the equation of state, and so on. Using the NRTL, we need to have some binary interaction parameters. So that means that we have a new tab here for binaries. And when you go to this binary, you can do some search directly from our databases. So you do automatic search, and then you will fill with the data which are stored inside our database. If you want, you can also estimate these binary interaction parameters using one of the predictive methods we have. So the Unifax, of course, but also methods like Cosmo if you want. So then you have selected the components, the model is described, and you have the binaries. Then you can use the services which are offered for the calculator, like for example the service calculation service. So here you have several calculations which are available for the physical properties, like transport properties and so on, or for equilibria calculation. What we are doing is that we will compute the bubble and the dew temperatures at the atmospheric pressure, for example, for the entire range of composition from pure water to pure ethanol. And then we will calculate. Here we have the results, so the bubble curve and the dew curve. You can also have here the equilibrium curves. That means here the vapor pressure, the vapor fraction, sorry, with respect to the liquid molar fraction. And you can add this axis, and you can do some zoom to see where is the azeotrope. If you want to add a new component, in that case, you will use add a new compound here. And when you click on this component, this is an empty component. Nothing is stored. And so you can provide him with a name, for example. And then if you provide a smile here, you can see that you will find here some symbol like this one. And if you click on that, it will predict the property. And you can predict all the properties if you want using this button here. And you can select for that several type of prediction methods. And it will fill all the fields which are here. Regarding the temperature-dependent properties, like the vapor pressure, for example, here, you can go to the regression button here, and then you have two choices. You can copy and paste some experimental data, but you can also predict your value here. Using a method. So here you have the predicted properties. You select the equation you want to use, for example, the deeper equation, and then you calculate and you do the regression. Here you have the results in terms of graphical results, and also all the results you have when you do the fitting. If you use this, you will have all the parameters which have been fitted. Okay. So now I will show you how you can access to these properties inside Microsoft Excel. So given that you can have several calculators inside same spreadsheet, that means that you have to rename first your calculator. In that case, for example, I will call it water ethanol NaCl. I will put the name here, and then I will access the properties. If you click on this button, you will see that you have new categories of function. For example, Simulis calculator. And here, you have all the functions which are available. For example, you have this function which returns the display name of a component. The first argument is the object name. That means which calculator you want to use, this one. And then the component index, this one. What is also important is to have the units which are used in your calculation spreadsheet. And here, I will go to select a function which is providing the units which are used inside Simulis Thermodynamics for the input system. That means for the, if I provide here the one value, this one, and the quantity. The quantity is the English name of the value, and if you want to find this quantity, you have here some help on the identifiers. You can also have access to all the properties which are stored for the components. For example, we can recover the critical temperature and the critical pressure. And we need, in that case, to know the identifier of these properties. These properties are phase change properties. So here you have the identifier for the critical temperature. I copy. And here for the critical pressure. And you have a function to have access to the property. Still the object name, then the compound index, then the property ID, then now we'll do the same calculation as the one we did previously in the calculation service. We'll do the bubble and the dew curve calculation. So first I will put the composition of the mixtures. I will do the calculation from 0 to 1 with a step of 0.01. Here I will compute the bubble temperature. I will put here the pressure for the calculation, and also the fact if I want molar or mass for the composition in entry in the output, and molar or mass for the results. So here you have the STKL bubble temperature to compute the bubble point temperature calculation. Still, I will provide the object name, then the calculation pressure here, then the composition type, 0 for molar, 1 for mass, and here the result type, same, 0 for molar, 1 for mass. And if you want, you can also provide some initialization value. When you use this function, in fact, if you go to the help, you can see that we explain what is the syntax for the function, what are the input parameters, the one you provided before, and then what are the results. That means the first one is a real value for the bubble temperature. Then you have a vector of bubbles for the liquid fractions, then a vector for the vapor fractions, and then a vector for the equilibrium constant. So we want to recover all these values. So this is X. And using Microsoft Excel, in fact, in order to recover several values from a function, you have to edit the function, select all the cells in which you want to have the results, and then to press simultaneously the Control plus the Shift plus the Enter tab. And then you can do the calculation. We do the same for the due temperature here. I will select the correct function. Which calculator I use, what is the pressure I want to use for the calculation, what are the composition, what are the composition type, and what are the result type. And then now I can plot the bubble temperature and the due temperature. Now, if you want to change, for example, the units for the output systems, for example, you change from temperature from degree Celsius to degree Rankine, automatically all the spreadsheet will be changed. That means the results for the bubble and due calculation, but also the value for the critical temperature and so on. And now if you, for example, build a nice spreadsheet, which can be used for many different systems, then if you come back to the calculator, if you change the calculation system you are using, for example, in that case, we will use the methanol instead of ethanol. We will change, for example, the model also. In that case, we use a predictive model like a UNIFAC modified Dortmund. When you use this kind of predictive model, you have to check if the parameters are available. So you have here a button, and in this button you can see the matrix which corresponds to the system you are using. Here you have the subgroups parameters for the van der Waals, volume, and area, and here you have the values for the groups, interaction parameters. Okay, and then I can come back to my spreadsheet, and in that case you can see water, methanol, and everywhere everything is changed. So it was a very quick overview of Simulis Thermodynamics inside Excel. If you want more explanation or information, you can come back to us. Isabelle?
This webinar, this is the end. So thank you for your participation. I hope it met with your expectation. We remain at your disposal if you need any further information about Simulis Thermodynamics or any of our process simulation software. A replay of this webinar will be sent to you probably next week. One more thing, after we hang up, you will be prompted with 4 questions about this webinar. If you don't mind, please just 1 minute of your time and tell us what you think about our presentation and help us improve our webinar. So thank you very much, everyone, and bye-bye and have a nice day. Bye.